Hello, I'm Yegor Prikazuk, and this is the user guide of SCOPE, Soil Canopy Observation of Photochemistry and Energy Fluxes model. Today we are going to talk about mSCOPE multilayer scope. What I expect you have already done is you went to our GitHub and you downloaded the model with download zip. After that, you have unzipped the file, and now you can navigate to Scope Master, and you see these files. Also, of course, you have MATLAB, which would normally start with double click of scope. See that the scope is open, and we run it for the first time. The first run has 100 simulations, and hopefully you get the same message that the output is the same as in the verification dataset, which means we are good to go. What I also expect you to do is to find our documentation. The link is directly in the README. In the documentation, it is explained here in mSCOPE because previously this model was separate, and this is still available at Page Young model developer repository as a standalone, but now it is integrated in SCOPE, so it's just enough to say set options mSCOPE equals 1 to run it. When will we need multi-layer scope, and what problem in scope does it solve? In default scope, all leaves have the same biochemical composition, the same pigments, and as a result, they have the same reflectance. Only VC max decreases with canopy layer exponentially with the KV extinction coefficient. But in real life, for example, bottom leaves of the canopy may be even not existent, or they may be already yellow. To account for this difference in leaf reflectance and transmittance, of course, we may change it per layer or per group of layers. And for that, mSCOPE was developed. I suggest you reading a paper of Pagey where the case of corn is illustrated and how different compositions of leaf reflectances lead to improvement of predictions of reflectance and also biochemical fluxes of this multi-layer canopy. However, radiative transfer is the same. So let's go to SCOPE and let's run it. First, we will still do it in a single simulation setup. So we go to input and we adjust set options, disabling verification, enabling single run, and for the time being, the mSCOPE option we also leave as 0, so we use normal scope just to see the difference. So we save it, we close it. If you want, you can adjust file names to say what is the name of the simulation. So it's a single run. Save it, close it, and in Scope Master 1 folder back in set parameter file names, we didn't change this file, but we will change the file name. So input data default is what we want to use. Save it, close it, run it. It's very fast, as you see. And in plotting, it says plot mSCOPE, but I'm going to plot the results of the default scope so that you can see the difference. So this is reflectance per leaf layer. It's not very obvious here, but if I type here leaf opt, you see that reflectance has, in fact, 2 dimensions. One is the number of layers, and the other one is the number of wavelengths. So here in scope, all leaves have exactly the same reflectance. That's why we see only one line. Now, let's go back to input, and in set options, we can enable mSCOPE. We say 1, save it, close it, and we go back to scope. We run scope again. You see, we took more time because this time scope was run twice. And if I plot the reflectance again, what I will see now are these 3 groups of reflectances. So some leaves, they continue to have our standard reflectance, and the other leaves had higher reflectance than it was before. Let's see why do we see 3 groups of leaves. For that, we have to go to input and there's extra file that we can finally open. It's called mSCOPE. The file is very simple. It says how many layers do we have in the model. Now we have 3 layers, and this, for each layer, we provide combination of spectral parameters, the parameters that affect spectra. These are leaf properties. I remind you, mSCOPE changes only leaf reflectance. So LAI here is indicative. This PLAI is in fact the proportion of LAI, which indicates at which depth of the canopy the reflectance will change from layer to layer. So can be treated as a proportion indeed. For example, here the total LAI is 0.5 plus 1 plus 1.5. So it's 3. So the first 1/6 of the canopy, because top is here, 1/6 of the canopy, 0.5 divided by 3, will have leaves of this reflectance. And then the 1/3 will have this reflectance. And then the remaining half of the canopy will have leaves with this property, so this leaf reflectance. So very important to know that the sum of these LAIs not going to affect anything besides the separation of the leaves. The upscaling of these reflectors of canopy with these layers is done based on LAI, in our case, in input data default. It is this LAI of 3. For example, if I say that here is 1.5, 1 and 1.5, so in total the LAI will be 4. The proportions change, but the LAI that will be used for upscaling is not 4, but it still will be read from here. It still will be 3. So it's very important to remember. So we have 3 groups of leaves. On the top of canopy, we have green leaves. In the middle of canopy, we have some pale leaves. And the bottom of canopy, we again have deep green leaves with a lot of chlorophyll, a bit darker. So if we look back to these profiles, we can see that middle reflectance is most likely for the top 0.5 number of leaves. Then we go down to very pale leaves in the middle of the canopy, and then at the bottom as very dark leaves. Such separation of reflectors has effect on flux profiles. As we know, and if not, then please watch the profile video. In SCOPE, we have a gap fraction probability of leaves being sunlit or shaded, if it's 1 minus this probability. So it decreases like that. And usually the profiles of default SCOPE are smooth. For example, this is profile absorbed photosynthetically active radiation for sunlit leaves, for shaded leaves, and the weighted sum. Then profile of photosynthesis, also quite smooth. Bottom leaves photosynthesize less, top leaves photosynthesize more. And the profile of eta, of the ratio between steady state fluorescence to the dark adapted state fluorescence. And if we go now to the multi-layer SCOPE, of course, the probability gap fractions are the same because LAI is the same, 3, but there is a break in between for all the profiles, especially pronounced in the profile of photosynthesis, because these are leaves with a normal chlorophyll quantity, these are leaves with the very low chlorophyll of 20, and these are leaves from the bottom with a chlorophyll of 80. So again, high ability to absorb photosynthetically active radiation. Now, let's adjust and let's say that I only want 2 layers of leaves. So what we have to do is we have to think and rebalance these columns. So for example, we can delete completely column, and let's say that in the upper half, like in the corner on my presentation, and the upper half, maybe 1/3, we have leaves, normal healthy green leaves. And in the bottom, let's say we have leaves with 0 chlorophyll, the dry leaves. And we also have to adjust the number of layers. So now I say that I need to have only 2 layers. This total LAI is indicative. So 1 plus 2 equals 3, but it doesn't affect simulation. We save it. For this simulation, I also recommend giving a name, for example, mSCOPE 2 layers, so that we can find the output. Then we run it again. We plot it because the output stays in the workspace. So leaves as expected. At the top, healthy. At the bottom, pale. And the profiles are as well as expected. At the top leaves photosynthesize, bottom leaves not. Top leaves emit some fluorescence, bottom leaves not. The last thing to mention, mSCOPE can also be used in time series mode. So we can set simulation to 1. File is located in folder dataset mSCOPE TS. The file is input mSCOPE time series, which consists of these columns. So it's the same as we see before. This canopy has 3 layers, and the first layer occupies 1/6 of the canopy with chlorophyll of 40, earthiness of 20, etc. So this file we have to read, and how we do it? In file names, first of all, we rename the simulation. So let's say we say scope TS. Second, we give the name of dataset dir. So it's a directory where mSCOPE input is, dataset space mSCOPE TS, but we don't use dataset, we only say mSCOPE underscore TS. And here is the special line 9, where mSCOPE CSV name has to be provided. mSCOPE CSV name is this one, so I just copy it together with extension and I put it here. Here, notice we say how many layers in this file are. In our case, 3. In contrast to normal time series run, we do not have to provide column names, and we have to provide all columns as they are here. So if we say there are 3 layers, so we have to provide 3 values of LAI, which is proportion at which reactors breaks, and then 3 sets of values for every parameter, even though it doesn't change. So this input is fixed. Therefore, here below, we have to delete all the column names, besides column T. And there's a small bug, but we have to also provide some file with column name T. So just for the speed, I'll provide the same file. But this is where mSCOPE input will be read from. So we can save it and we can run scope. There will be 4 simulations: 1st of January, 30th of January, 10th of March, 9th of April, and there will be some warnings that the column T was treated as a day of year, and the year was provided as 2020, and midday was used to calculate solar zenith angle. As a result, it's day 1, day 30, so January 1st, 30, and then March and April. The output is stored as always in the output folder, mSCOPE. And for example, if we look at the vegetation, we see that, for example, gross photosynthesis was increasing. It is possible to set here another file with the meteorological data if it was changing, and then the values will be interpolated. For this, how to do it, you may watch our previous video on scope time series run. So now you know how to run mSCOPE multilayer scope, providing parameters that will result in different leaf reflectances and different heights of the canopy, and that will have vast profound impacts on the fluxes that we are simulating. Furthermore, this can be run in the time series mode. See you in the next videos.